Welcome to our first screen lesson, chemistry students. This lesson is on a note that you may wish to print off if you don't already have it. The 3U students got it on the last day before March break and our school closure. 4C, if you want to print it off, it is in our class notebook. Otherwise, the finished version of the note will be available in our class notebook after this lesson. So as we go through the lesson, remember you can pause the video at any time to complete questions or take notes. So I think we will begin. So in both of these chemistry classes, we're starting quantitative chemistry, which basically means we're going to be doing calculations with chemistry units, I guess. So there's just some basic math skills that you're going to need to be more successful in this unit. So hopefully a lot of this is review from other classes. And if so, we'll just brush up on it. All right, so the first thing we're going to talk about is significant digits. Significant digits, when you look at a number, basically shows you how accurate the number is. And because a lot of the data you'll use when you're doing a calculation in chemistry is taken from a measurement, quite often a scale, for example, the scale had a limited amount of accuracy. So expensive scales, for example, can measure to the thousandths of a gram, whereas a cheaper scale might only do to the tenth of a gram. So the more digits you see in a number, the more accurate it is. The reason we have to be able to figure out how many significant digits something has is because after you do a calculation, you cannot end up with an answer that is all of a sudden more accurate than the measurements you were starting with. All right, so to count significant digits, the only thing that's weird is zeros. Pretty much zeros count, except in one situation, and that is if they are preceding or to the left of when other kind of real digits begin, because those zeros are just acting as a space holder. So we don't count them. The other thing you need to keep in mind is some numbers are considered like 100% accurate. Things like conversion factors, and I have one here that 1 kilogram is 1,000 grams. That is like 100% accurate. So we say it's infinitely accurate, or has an infinite number of significant digits. And that is the sign for infinite. Another situation can apply if you're counting things. You're a good counter, you're counting things that are easy to count, you did not make a mistake. So for example, if I looked out into the classroom and saw 33 students that were all sitting in their desks and I counted them, I could be, pretty much 100% sure that I had an accurate count, and therefore it'd be infinitely accurate. Okay, so let's look at these two examples here and see why the answer is 5 significant digits. So as I mentioned, we're not going to count zeros out front because we're going to see that they are just holding a place. So we're going to start at the 1, 2, yes, that 0, 8, and that 0. So 5 significant digits. Here we're going to count the 9, the 2, the 3, and the 0 at the end. Okay, so 4 significant digits. We'll do a couple of these to practice, and then I'll leave a few blank that you can try on your own and then look up the answer sheet to check your work. Okay, so 70.00 grams. Remember, zeros after are important because they are really showing you how accurate that scale was. So we're going to count all of those digits. So we'll have 4 significant digits. This is a funny one, 345 atoms. It kind of sounds like somebody counted 345 atoms, but realistically, we know we can't even see atoms, so there is no way we could have counted them. So this is not infinite. This is 3 significant digits. Okay. This one, 0.0000, all just space holders. Start counting at the 5 and then count everything after. 3 sig digs. Now I think I'm going to jump over and just do this one here and leave a few for you to finish on your own. 1,000 grams per kilogram. This example is exactly what I put up here as an example, that 1 kilogram is equal to 1,000 grams. So that is what we call a conversion factor. It's just like saying, you know, there's 60 seconds in a minute, or there's 10 millimeters in a centimeter. They are just 100% accurate. So here we're going to put infinity. Okay, so I'm going to leave those for you to practice because you will be doing a quiz on these skills. All right, so once you can identify how many significant digits you have in a number, there are times when you are going to have to, after doing a calculation, you're going to have to round off your answer to reflect a specific number of significant digits. You don't want to be writing down, you know, that giant number that shows up on your calculator screen where the whole screen is filled with numbers, because that's ridiculous and is implying that your answer is much more accurate than it really is. So you have to know how to round off. We're going to do very easy round off rules. When you know how many digits you want to keep, simply look at the next number and then make a decision. If it is smaller than 5, you're going to chop off everything. If it's bigger than 5, your very last number is going to go up by 1. So these examples, we're going to round to 3 significant digits. So we want to keep the 1, the 0, and maybe the 2. That's 3 numbers or 3 significant digits. In this case, 4 is smaller than 5, so you're just going to chop. Okay, and therefore you end up with 3 significant digits. Here, we're not going to count those zeros out front because we don't. So we want the 3, the 4, maybe the 8. But we look at the next number, 7, bigger than 5. That pushes our 8 up to a 9. So this one we did a round up. All right, so in our practice chart, I've made a variety of numbers of significant digits that we might wish to round to, just so they're not all the same, because every question is different. So if we wanted 4 significant digits, and this is what showed up on your calculator, you'd want to keep the 7, the 3, the 9, maybe the 5. Look at the next number. It's bigger. That pushes the 5 up to a 6. So 7, 3, 9, 6. And then, of course, we need to include the units. On this worksheet, I have lots of units, and some of them will look familiar and some not so much. Grams you will be familiar with, but moles maybe not, but you sure will be by the end of this unit. So I don't expect you to necessarily know what unit to use for an answer while we're doing this. That is something we'll address in the next couple of lessons. Okay, 3 sig digs. Ignore those zeros out front. Start counting at the 4, 7, maybe the 2. Look at the 4. We're going to chop. So we're going to have 0.0472 moles. And that has 3 significant digits. Okay, we'll do one more. So this one I only want 1 significant digit. So I want just one whole number. So should it be a 2? Should it be a 3? Well, because the next number is a 6, it should definitely be a 3. And that will be 3 moles. Okay. So hopefully you can finish those last 2. Now, in chemistry, we will be doing some calculations, and 95% of the time, we're going to be multiplying and dividing, okay? But occasionally, we will need to do some adding. Rarely subtracting, to be quite honest, but definitely some adding when we do molar masses. So when we add numbers, suddenly we're not actually even concerned about significant digits. It's all about how many decimal places there are, which means how many numbers appear after the decimal. So the one thing that is common about adding, subtracting, multiplying, and dividing is your final answer is always concerned with like the least number of either decimal places or significant digits that was in your data, because remember, your answer can't magically get more accurate. So you should follow along on your calculator to do these. And I recommend that whatever calculator you start using in this course, you should try to always use it, because you'll get to know how to press the buttons in what order, etc. that works, because different brands are different. So I totally expect you can all subtract these numbers, but just do it anyways. And what you're going to see on your calculator is this number, 128.25 grams. Okay, that's not what I'm testing you on. What I am curious about is, can you get the final answer, which is that. And final answers we like to write in a square box, makes my marking a lot easier. So why is it this? Okay, so if we look at the one piece of data, it had one decimal place. The other piece of data had two decimal places. Which one was least? 1. So in your final answer, you had to end up having one decimal place. So you wanted to have one number after the decimal, so you looked at the 5 and pushed that up to a 3. Okay. Second example, we're adding some stuff. So again, try this on your calculator. 1.15 grams plus 2.13 grams plus 6.187 grams. We've got 2 decimal places, 2 decimal places, and 3 decimal places. So hopefully you are recognizing that your answer is allowed 2, because that is the least number of decimal places. This is what will have popped up on your calculator, and then you are going to say, okay, I want to keep the 4 and possibly the 6, but I'm going to look at the 7, and that makes my 6 turn into a 7. And then just put a little square box around that final answer. So multiplying and dividing is what you really want to focus your attention on. So now we are worried about significant digits. So here's a practice problem. Try this. 6.1 grams divided by 10.81 grams per mole. There's a unit you won't be quite familiar with just yet. Now, what I've wrote here is actually not what's on your calculator. Your calculator is going to be full of numbers. After the 0.5642, you'll notice you even have a 923 after that. I didn't write it down because I can tell very quickly by looking at this that I have 2 significant digits here, 1, 2, and I have 4 significant digits here. So my answer is only going to have 2. I jotted down 4, which was plenty. I could have actually just jotted down 3, because technically all I need to look at is that third number to make a decision. So this was lots to put down at first. I want to keep 2, so I'm keeping the 0.56, but I'm using the 4 to decide if I'm keeping the 6 or not. And I am, because 4 is less than 5. Okay. And here, try this. Again, you actually get this on your calculator. Okay, but again, no need to write all that down. Here we've got 3 significant digits and 5 sig digs. So we're allowed 3. So by writing down even 227.5 would have been fine, because you're going to use the 5 to make a decision to push that 7 up to an 8. Okay, so on the back I have some practice for you. I think I might do, let's see, We'll do 2 questions, I think, together and leave 2 for you. So I'm going to leave that adding one for you. Remember, that's all about decimal places. And we're going to do this one. So 5 grams divided by 54.94 grams per mole. Please do it on your calculator. And you're going to get, well, again, a big calculator screen full of numbers, that's for sure. Now, again, I'm looking here and I can see I have 3 sig digs and I have 4. So my final answer has to have the least. It's going to have 3. So I should probably write down, you know, a little bit more than this because I'm going to be looking at 910 and my next number was a 0. This unit is moles. Don't worry about that at the moment. Okay, so 3 significant digits, not going to count those. So 0.0910. And that is it, because I'm going to look at that 0 and say, yeah, I'm just going to chop it off. Now, in the next section, we're going to look at how we could actually tidy that up and make it look a little nicer. And that would be called scientific notation. So if you're familiar with that, you can do that now. Otherwise, we'll just wait. All right, so here I've got 34 molecules of water. And every molecule of water has 2 hydrogen atoms. We could even think of this as 2 H atoms per 1 molecule of water. Okay, so what we're looking to figure out here is how many hydrogen atoms do we have. So this is 2 significant digits. And 2 hydrogens in every piece of water is infinite. Okay, so that's never going to change. That's the law of constant composition. So on your calculator, you will get 68 atoms of hydrogen. That's literally what it's going to say. And that is good because infinite and 2, smallest is 2, 68 fits. Okay, I'm going to leave the last one for you. Okay, so scientific notation. This is used, well, we'll use it for 3 reasons. To make really big numbers, like reasonable to write down, such as Avogadro's number, which is something we're going to be using in chemistry a lot. It has a lot of significance. This is what it looks like. It's huge. Okay. If we use scientific notation, we can write it as 6.02 times 10 to the 23, because essentially from 6 decimal, oops, push too hard there, over to here, if you counted all those spots, there would be 23 of them. Okay, so it cleans up really big numbers, can also be used for very small numbers. So like a tiny little mass here, you know, 0.000045. So if I again counted all those spots, I would have 9 spots in between where the decimal was and where I have now placed it. So you're going to have to use scientific notation occasionally when you're trying to write an answer with a certain number of significant digits. You might be forced into having to write it this way in order to express those significant digits. But it's just also so much easier than writing huge and tiny numbers. Now, the number that is multiplied by a power of 10 is always a number that's between 1 and 9. It can be 1 point something or 9 point something, but it's never going to be like 10 point something. So it's going to be between 1 and I just put 9.9 just to give you an idea that you would never actually step it up right to 10, but it could be 9.99999. That would be fine. All right. Let's do a couple. That's the easiest way. So in this chart, I've actually asked you to do them all with 3 significant digits. They don't have to be that way, but that's just what we're going to do for examples. So here we've got 300,000. currently the decimal is sitting here. If we're putting it in scientific notation, the decimal is going to have to go after the 3. Why? Oh, I keep pushing too hard. Because we want to have a number that is between 1 and 10, like 1 and 9, right? So it's going to be 3. So if you kind of jot that down, that can help to get you started. And then you'll notice that if you count everything in between where the decimal was and where you put it, you will find that there was 5 spaces. It doesn't have to be zeros, just five digits. So 3.00, that's our 3 significant digits. And then it's going to be 10 to the 5, 10 to the exponent 5. So then that way you can tell it is a very big number. And 300,000 is a big number, so it does need to be 10 to the 5, not -5, because that would be a tiny, tiny number. Here's one where we'll use a negative exponent. So 0.0046. I want that number between 1 and 9.99. So my new, oh goodness, my new decimal has to go right there. So it'll be 4.6. So if I count up, I've moved it 3 spaces. Now my number with 3 significant digits is going to be 4.63 because I'm looking at the 2 and using the 5 to decide that my 2 is going to become a 3. And then I've moved it 3 places, but notice how in this case, I made my number bigger. So if I had a tiny number and now it's all of a sudden, 4, I made it bigger. So I need to express that in my answer and say, no, it's actually a small number. So it's going to be to the -3. Okay, here's a huge number. So huge numbers end up having positive exponents. So my decimal is initially here. I want to place it here between 8 and 8.9, so it'll be something less than 9.9. And then I count my spots. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I need to have 3 sig digs when I write it. So 8.9, should I keep the 4? No, 7 tells me to make that into a 5. And that is to the exponent 9. We'll do one more, leave a couple for you. Okay, so all those zeros are space holders. So this is an example of like why those are just space holders and they can go away, because as soon as you write it in scientific notation, they're gone. So I want 8.5 and 1, 2, 3, 4, 5. And it's going to be 8.50. Now this was a tiny number that I turned into a number 8. So I need to use a negative exponent to show that it is a small number. Okay, calculations. Now these are special calculations where we're going to have these ugly exponents. Because of the fact atoms and molecules are so tiny, we are frequently dealing with huge numbers. Often this 6.02 times 10 to the 23, which is called Avogadro's number, is very common. So some of you will have no trouble using your, Casio or Sharp calculator to actually put this calculation in. 4.5 times 10 to the 2, and you're going to multiply by 6.02 times 10 to the 23. And some of you will get this final answer. And if you do, fantastic. But if you are having trouble getting along with your calculator, don't despair. I'm going to show you this method. I like to call it the cheater method because basically you can get the right answer without using your calculator. And it makes you not have to put those exponents in at all, because depending whether you have a Sharp or Casio or Texas Instruments, you may have to use brackets, but they're not even all the same of how when and where you put the brackets in. So I can't give you a set rule. So this is what you can do instead, which is super easy. You're just going to take the number, so the 4.5, and the other number, the 6.02, and do the operation between those two numbers. So they're supposed to be multiplied. So I multiply them. This is what pops up on your calculator. Okay. Then the exponents I deal with separately. So the 10 to the 2 and the 10 to the 23, I just deal with those in the second step. And when you multiply, you add them up. So a 10 to the 2 and a 10 to the 23 is 10 to the 25. Then just smush your two answers together. So 27.09 times 10 to the 25. That quantitatively is the correct answer, but it's kind of disobeying a few of the rules I've been trying to teach you today. So first of all, we don't have the right number of sig digs. We had 2 and we had 3. We're allowed 2. Okay, so 27, look at the 0, just keep 27. Now the other problem is we would never write scientific notation as 27 times 10 to the 25. Computers wouldn't like it. I will forgive you, but if a computer is marking the question, it's not in the correct format. It needs to be a number between 1 and 9.9. So remember, 27 has the decimal here, so you're going to move it one place smaller to make it 2.7. And if you move it one place smaller, then your exponent needs to become one number bigger. So that's why it becomes 26. Okay, so when you divide some exponents, you just subtract them. So same thing, we're going to deal with just our numbers, 5.89 divided by 6.02. I think this is what you're going to see on your calculator, that number there. Now we're going to deal with the exponents separately. So 10 to the 26 and 10 to the 23. Because the 10 to the 26 is being divided by the 10 to the 23, the 26 subtracts 23. And what you're left with is just 3. So put our two answers together, the number answer, the exponent answer, and then we clean it up. So in our original question, we had 3 sig digs in both our measurements. So we're allowed 3, so we could at first say 0.978, but again, we're not obeying our scientific notation rules. So it's correct, but it's just not tidied up enough yet. So let's move that decimal one place. So we had 0.9, now we've made the number bigger and turned it into 9. So your exponent becomes smaller. Okay. So there's 3 practice questions for you to do here. We could just do the first one together. Okay, so we've got something with 3 significant digits and something with 2 significant digits. Because we're multiplying, so we're not worrying about decimal places. We're definitely doing sig digs. So on the calculator, 6.02 times 7.8, and you are going to get 46.956. Okay. And then we're going to say it's 10 to the 23 times 10 to the 5. So we're going to add those. So that's going to be to the 28. And then we're going to clean it up. So it's going to be 3 significant digits. And we want, okay, we're going to have to back up here. Sorry, we want 2 significant digits. That's my mistake, I apologize. So we want 47, because the 9 makes us go up, times 10 to the 28. Clean it up. 4.7, we made that smaller, so make your exponent bigger. Okay, and that is it. Please finish up all of the questions that we've left blank and then check your answers. Thank you for tuning in.